Well, now it's time to talk how to transform an analog signal to a digital signal. Can you spot the differences between these two pictures? The first one is an analog representation of a signal, and the second one is its digital counterpart. I'll give you a little hint. Just look these 2 points, A and B, in the analog case and in the digital case. Basically, the most formal way to describe the differences between the two is that to go from A to B, you have to pass infinite points of this curve, while in the digital case, going from A to B, you need to step over a finite number of points. This is important because to represent a signal in a computer, you have to discretize it, because an analog signal contains infinite information in some sense, while the digital signal has a finite number of information. This because your computer is a finite object. It has a finite memory. And how do you store those points? Those points are equally spaced on the x-axis, so it could be useful to represent a signal x as the sequence of its y values, which is something like this. So it's an array, it's a set of numbers representing these symbols, these points. If this is a sound, this represents the pressure the sound should take. If it is an image, it represents the brightness it should take. And if you want to process, to do some effects on this signal, you just apply math to those numbers. For example, if we multiply all those numbers for a constant, in case of sound, we change the volume of that sound, or in case of images, we just change the brightness of images. The operation of going from here to here is called analog digital conversion, and the opposite operation is called digital to analog conversion. Let's see how this happens. First of all, you need to sample the signal. That means that in a regular interval of time, you have to look the value of your signal and keep it hold while you measure its value. This is important because it transforms an infinite set of time instants into a finite set of time instants. So it's the end of infinity for time. They become a finite set of time points you have to store. But as you can see, this wave does not resemble the first wave. It is very distorted and it is something strange. So if you hear this wave, it should sound very different to this wave. Fortunately, there is a theorem, a famous theorem, that tells us that if the frequency you pick these values is greater than twice the maximum frequency of this signal, then you can reconstruct the original signal simply by smoothing this shape. Otherwise, you introduce a noise called aliasing. So, for example, if you have an original image which is this big, or it's the analog representation of the image, if we sample it with an insufficient resolution, so with the sampling frequency which is not twice the details we want to store, we will see some images that are not present in the original. This is aliasing. This is called aliasing noise. Let's hear this, its sound counterpart. This is the original signal. And this is the signal sampled with an insufficient frequency. You can hear some harmonics, some frequencies that are not present in the original sound. And this is the aliasing effect. But if we resample it with a sufficient resolution, we can see we have just a smaller version of this one with all the features preserved without any noise. And also the sound sounds almost identical. This is because we have enough resolution to come back to the original sound. But reality has way more details that we can store inside a computer. So how can we sample reality without introducing aliasing? Well, we can do this thanks to anti-aliasing filters, which is basically a filter that smooths the image and removes all the details we cannot see, and then we can resample it without those details. Well, we end up with a finite sequence of numbers, okay? So we have a finite sequence of number, we could store it inside a computer. But there is actually one difference between the numbers we are handling now and the numbers we want to end with. Can you spot the difference? You can see this number has just one decimal digit, while these numbers have many decimal digits, even infinite decimal digit. It means that in this case, we have a finite set of numbers with an infinite precision, while here we have a finite set of numbers with a finite precision. Our computer has a finite memory, and this memory is made of small blocks, each with a finite size. And we basically have to round up these numbers according to a certain precision we are aiming. This operation is called quantization. So it's basically discretizing not time, but the possible values that the signal can take. Unfortunately, unlike sampling, in quantization, there is no magic formula that tells us that we can come back to the original signal. It doesn't matter how many small those steps are. It doesn't mean how many digits we can take. So if we quantize a signal, when we come back to the analog domain, you can see that the red line has some difference with the blue line. Those differences introduces what is called as quantization noise. And quantization noise cannot be avoided. It can be reduced by picking a large number of digits, so a large precision for quantization, but it cannot be avoided. But there is a technique which is called dithering that let us hide the quantization noise. It's not removing it, it's just hiding it. Let's see what does it mean with both images and sound. Here we have our non-quantized picture with our non-quantized sound. And here we have a quantized picture or the quantized sound. As you can see, the reduction of a number of bits, it's something that reduces the possible brightness values of our image and divides it into bands. But if before quantizing we add just the right amount of noise, the number of colors is reduced, but the error is spread around the image. And so our brain is tricked to think that this is a smoother image than this. Let's hear the sound counterpart. So basically what dither does is masking the distortion of the image into a noisy background. It turns distortion into background noise, which again is not avoiding quantization noise, it's just masking it. For this reason, dither must be applied just when you are sure you're not going to touch your signal anymore, because adding a noise in a signal that in the future will be manipulated, raised in volume, distorted, or processed in some way, will basically blow all your noise around the signal. Finally, once we sampled our signal and we quantized our signal, we can have a digital representation of our signal. But you probably noticed that in most cases, we are equipped with 2 ears and 2 eyes. Moreover, our eyes have 3 different color receptors. How does this fits into the digitalization process? Well, since we have 2 ears, usually we record the stereophonic audio. That means that we record 2 signals for audio. One that is aimed at the left ear and one that is aimed at the right ear. And this provides us the impression of sources that are not just in front of us, but are all around us. You probably tried 3D cinema. It is just letting the left eye see something and the right eye see something else, just as we do in reality. And this is useful to trick our brain into thinking that we are seeing something three-dimensional with a depth. When we take a picture with our cameras, we usually take a monoscopic picture, so there is no depth. But if we could take stereoscopic pictures, we could perceive the depth of the picture. And what about colors? Also, colors can be considered 3 different signals aimed at providing an illusion of color. We have 3 color receptors, one for red, one for green, and one for blue. So each color image you see is actually made of 3 different images, one for each color receptor of your retina. These different signals are called channels. So in a stereophonic audio, we have 2 signals that correspond to 2 channels. In a stereoscopic pictures, we have 2 channels, 2 image channels, while in monoscopic picture, we have just 1 image channel. And in color images, we have 3 color channels images, actually. And all of these signals are stored, as we saw previously, with this technique, the sampling and the quantization process. Just as a recap, let's now see which are the typical parameters of the sampling and quantization for a different kind of signals. So, sounds, the informative unit we sample, the number we store on the computer, is the pressure level of the sound, and it's called audio sample. When we have 1 channel, we are talking about monophonic audio, so it's equal for both ears. When we have 2 channels, we have 2 signals stored, and it's called the stereophonic audio. When we have more than 2 channels, we talk about surround audio, which is audio that can be perceived from all directions, which is very immersive. The sampling we do on audio is a temporal sampling and defines the maximum frequency content we can have inside our sound. And the quantization operates on the dynamic of the sound. If we quantize with more bits, that are the digits used by computer, if we quantize with more bits, we have more dynamic range, so we can have more difference between low volume sound and high volume sound. If we have a low number of bits, we have a lower range in which we can move the volume before falling into quantization noise, before being masked by quantization noise. For images, we have the pixel, which is the number you store for each sampling of the image. We have 1 channel for grayscale images, 3 channels for color images, which can mean red, green, and blue, but the color can be represented also in other ways. Or we can have a 4 channel when we talk about color, plus a transparency channel that tells where the picture is transparent and when the picture is not. The sampling of picture is spatial, so it's basically its resolution is a dot per inches or a pixel per inches or megapixels. And the quantization operates on colors. The more bit you use to quantize an image, the more colors you can represent. For example, if you use just 1 bit for quantizing an image, you just have 2 colors, which is black or white. And finally, video, which are basically a sequence of pictures. So the informative unit is the frame, which is the single picture. We can have a monoscopic video, just like images, or stereoscopic videos. And the sampling is a temporal sampling, which is basically the frame per second. And of course, each frame inherit the sampling and quantization properties of single pictures. Let's see the typical values for sampling and quantization of real-world signal. If you remember the last image we saw in the first module, it was our hearing space. That means the frequency range we can hear. And if you remember correctly, we can hear up to 20 kilohertz. So if the sampling theorem we saw tells us that we must sample a signal more than twice the maximum frequency we are interested in, if we are interested in listening until 20 kilohertz, we must take a sampling frequency greater than twice 20 kilohertz. It means greater than 40 kilohertz. For this reason, usually we use 44 and 100 hertz. But we can also use greater sampling frequencies if we want to handle the signal in a more precise way. For example, we use from 2 to 8 channels at these sampling frequencies at this quantization resolution for processing audio, to work with audio while we produce our content. And then when we distribute our audio, we can fall down to 2 channels at 44.1 kilohertz at 16 bits for producing, for example, a CD or a video. For pictures, we usually use 3 channels, 3 color channels at 300 pixels per inch with 8 bit of quantization per color channel. And for video, there are plenty of formats. You can pick the one that better fits your needs. So just to make a recap of what we saw in this module, we learned how signal is turned into the digital domain, first by sampling, which is an operation that will let you not to lose information if you use a sufficient sampling frequency. Otherwise, you end up with aliasing. Quantization, which is something that always introduces some quantization noise, but this noise can be masked with a technique which is called dithering. We saw how many channels per signal we usually store, and we saw some common conversion parameters. If you missed something of these topics, please watch the video again.